Hi everyone, welcome to RhikInfo. Today let's decode few concepts in physical chemistry, focusing on graphs and its interpretation. This video presents a graph master table and order sheet covering solutions, electrochemistry, and chemical kinetics, summarizing essential graph types and orders. Let's review vapor pressure and Raoult's law. Pay attention to how mole fraction relates to vapor pressure, the shape of the resulting graph, and its interpretation, including deviations from ideal behavior. Raoult's law gives linear graphs for ideal solutions. Here we analyze colligative properties. Key relationships involve molality versus elevation, or depression in temperature, and concentration versus osmotic pressure. Colligative properties follow proportional relations, hence straight lines pass through the origin. Next, we look at azeotropes and boiling point composition. Note the distinction between minimum and maximum curves corresponding to positive and negative deviations from Raoult's law. Always recall straight line means proportionality, curve means deviation, extremum means azeotrope. This summarizes the important relations for solutions, including equations for freezing point depression, boiling point elevation, osmotic pressure, and various aspects of Raoult's law. Moving to electrochemistry, we examine the Nernst equation and thermodynamic relations. Observe how E cell changes linearly with log Q and its dependency on temperature and log K. This section focuses on Gibbs free energy relations. Straight-line graphs illustrate the inverse linear relationship between cell potential and Gibbs free energy. Higher E0 means larger K and greater spontaneity. We explore conductivity and molar conductivity. Graphs show the change in specific conductivity with concentration and the linear and curved behavior of molar conductivity for strong and weak electrolytes. Weak electrolytes show curves due to ionization on dilution. For cell potential and concentration cells, notice the straight-line relationship for concentration cells and how E cell approaches zero as the reaction progresses toward equilibrium. Now let's cover electrolysis relations. These graphs demonstrate linear relationships for charge over time and mass deposited as a function of time, charge, or current, confirming Faraday's first law. Remember Nernst, Gibbs, and Faraday's equation electrochemistry graphs become easily predictable. This relation summary for electrochemistry lists key equations for cell potential, equilibrium, thermodynamics, conductivity, and Faraday's law. Moving on to chemical kinetics, we study integrated rate law graphs for order identification. Straight-line plots of concentration, log or reciprocal concentration versus time determine the reaction order. You needn't calculate reaction order, you recognize it from the graph. Next are rate versus concentration graphs. The shape of the curve, from horizontal to parabolic, indicates the reaction order, and the slope of log rate versus log concentration gives the order. Here we look at half-life relations. The dependence of half-life on initial concentration distinguishes zero, first, and second-order reactions. Arrhenius equation graphs relate the rate constant to temperature. Linear plots of ln K or log K versus 1/T allow for the determination of activation energy from the slope. Energy profile diagrams illustrate reaction pathways. Important concepts include activation energy, the effect of a catalyst, and identifying the rate-determining step in multi-step reactions. Thus, graph identifies order, half-life confirms it, and units of K verify it. This summarizes key relations in chemical kinetics, including general rate law, integrated rate laws for various orders, half-life equations, and the Arrhenius equation. Here is a master quick flow for graph analysis. Key takeaways include using the slope of straight lines, recognizing log terms for first-order reactions, and linking E cell versus log to the Nernst equation. More quick flow reminders. Use integrated rate laws when time is given. Understand extrapolation. Check activation energy for temperature changes, and always match units. Critical cautions include applying the Van't Hoff factor for ionic solutes, selecting the correct R value based on units, balancing redox reactions for N, and remembering E0 of cell is never multiplied by coefficients. This is RhikInfo. Thank you for watching this video on physical chemistry graphs, concepts, and interpretations. Stay systematic, stay confident. All the best for your board exams. Bye.